Hello everyone, can you hear me? Okay, good. Today we will talk about um, the assembly language, and we will introduce the set of language to you. But before we're doing that, let's just quickly go over what we have been talking about last time. Bear me like 5 seconds. Okay. So last time we talked about the binary, the Boolean algebra, the bitwise operations. We talked about um, how we can use a bitwise operation to manipulate the, the binary number. And the part we talk about doing the bitwise AND, that is to set a bit to be 0 or keep the bit. And if we do OR, we set the bit to be 1 or stay the same. And for XOR, that's the place we want to flip the bit. It comes to XOR to do this job. And we also talked about several cases and how we can manipulate some bits. And also we talked about the logical operations. For the logical operation, we have the true or the false. And in our computer, we have the 0 to denote false and the 1 to denote true. And when we evaluate the expressions, if we, by looking at the beginning of the expression, if we could determine the overall value for it, then we stop right here and will not execute the following part. In this case, we will just print out the logical results. We don't even execute the printing because overall the logical expression, when we look at the first part, it's already true. So we know there's no need to execute the function afterwards. And also we talk about shift. Logical, when we shift to the left side, there's no difference between logical and arithmetic shift. But we want to shift to the right. If it is a logical shift, then we just fill the empty space with 0. If it is arithmetic shift, then we'll fill the empty space with a sign bit. It's either 1 or 0. And in our C program, if the number already is a variable is a signed number, then the shift would be arithmetic. If it is unsigned number, then the shift would be logical shift. And this is what we talked about last time. Today we will introduce the assembly language. Okay, before we start this chapter, just a quick announcement. Because of my personal schedule and family reasons, we will have the in-class from Thursday for like 3 or 4 weeks. Basically, I need to move the online time to a later part of the class. But yeah, we will. So next class we will in class, in person. So just a quick announcement, and I will update the schedule afterwards. Okay, let's go back to the content. Here we will talk about assembly language, and we will first talk about assembly in a history perspective. So this example about how the computer looks like many years ago. around 7 days, 8 days, 7 days. We just have this big box. And, we don't even have the keyboard. What we have is you can see there's some buttons over it. And then when you click that button, that is to input 1. If not, that means a 0. So by using this board panel, we could input our program by this way. It's binary, right? Click it or not, it's binary. This is from this part, we can see the right side of this code, the number 4889, things like that. What we call is machine level code. And here's an example for Hello World. This binary code we can literally input using something like the machine we talked about. If it is 1, then click it. If it is not, it's 0. By such a way, we can give the machine level code to the computer, and the computer can run it. That's machine level code. It's binary. And now we don't have this. Don't have our computer don't have such a panel and don't have these clicks, but it works in quite a similar way. It is electronic signal. If it is 1, we send out the high voltage. If it is 0, we basically keep it low voltage. And then in such a way, it is passed through the machine level code to the CPU or whatever to try to execute it. So the machine level code is something that a machine can understand. It is binary, and if it is high voltage, if it is 1, then high voltage is low voltage. So it's binary. Binary is the machine level code, and a machine can understand this without any trouble. It's 1 and 0. And we can put ourselves into the shoes of the programmers dates back to 1960s, 1970s. They have to write the machine level code. They have to put down these 1 zeros, and they have to click that buttons. And they have it's quite a burden to remember this binary, right? You're not remembering any human meaningful letters, words like C program. You are just remembering a lot of binary 1010s. For the programmers at the moment, it's just something you have to remember. Here comes the assembly. We want to make the job of the programmer much easier. What we can do? We can we hope to assign meaningful words to this program so that it's easier for our human to remember. So here is an example. You can see there is a 4889. Previously, we have to remember 4889 is the binary combination to move the data from one place to the other. Now, what do we do? 4889. Now, what we do is we just name the 4889 to be move Q in our example. We just name it. In such naming process, naming the binary machine level code is called this. Is there any questions? Okay, let's continue. So that's naming process is called assembly language. And now for the programmer, the assembly language programmer, now it doesn't have to put down 4889 or even to remember 4889. It just put down move Q, right? To denote such such a thing. And for another one, 4889, you can see it's still move Q. It's 488B. Weird. So anyway, so so in such a way, we can write down a program like this, and we don't have to write the machine level binary programs. For the right side, that's assembly. That's assembly. We don't have to remember 4889. What we need to remember is move. Anytime we want to move the data. We don't have to remember FF. We can just put down call to know that, to make a function call over it. So we just naming the binary. By such process, we have the assembly language. And this is the very step we have a language which is closer to our human, but one step further from the machine. So machine have no problem about the left side binary numbers. Anytime see 1, then that's high voltage, see 0, then lower voltage. If you give these electronic signals into our computer, we can do things accordingly. But when we move to the assembly, the good thing about it is, as a programmer, we don't have to remember numbers. We just need to remember move, call, XOR, things like that. That is easier to remember, easier to use. But the drawback is now our computer cannot recognize the assembly language directly. Let's say MoveQ. We want our computer to execute MoveQ. How we can do it? Computer have nothing, no understanding about MOVQ. Any letter, it doesn't make sense to the computer. Computer is just a machine accepting high voltage, low voltage as a 1 and a 0. So right now, the assembly doesn't make sense to the computer. What do? We need to have a translator in between. That is what we call assembler. For the assembler, you just look at this assembly code. Anytime when it sees MOVQ, it checks the mapping between this MOVQ and the number. And we just basically what we do is just a reverse process. When we look at the MOVQ, we just go back and find out what should be the number corresponding to the instructions. In this case, is 4889. We basically substitute the MoveQ with 4889 so that we go back to the machine level code, and in such a way, we just have something that a machine, again, being able to accept and understand. That's where the assembler looks like. And the reason we don't have a class called assembler is because such process is quite straightforward. So you may construct your own assembler. Every time you see a move Q, then you have the mapping to 4889. Every time you see a call Q, then you map that back to FF. Right? You can imagine for assembler, it's just a mapping between the name and the number. So it's quite a quick substitution if you want to translate assembly to machine level code. So this is just what assembly is, and we need an assembler to translate assembly back into the machine level code. Here we just quickly review. We talk about what assembly does, and here we just quick review about the higher level programming language and what it does. So when you write down C, C++, Java, Python, the high level programming language, we daily use it. And when we try to compile, apparently our computer cannot understand this even higher level language. We cannot understand that. What we do is first we need to convert the higher level programming language into something assembly. This is the first step. And the translator in between is called as a compiler. So the compiler look at your higher level language, let's say C++, C, and then find whatever in it, if else, do while, function call like that. It will look at assembly. It will look at this C program, let's see, and translate that into the assembly language. So the assembly language, and based on the assembly language, we further use the assembler to translate back to the machine level codes. And the machine level codes will just be an enormous collection of 101010, something that a machine can recognize, but at this point, our human cannot. In the machine level codes in our system, sometimes they are called as a executable file, something you can execute, and it should be binary. Right? This is we relies on several translators to build the bridge between the higher level programming language and the last step machine level codes. In between, we need to translate higher level to assembly, then by the compiler, and then by the assembler, we further translate them to the machine level codes. This is basically how our language, the programming language, works. Not surprisingly, higher level language is more towards human readable side. So higher level is more readable than assembly. But the drawback is we need another layer of translation. That's something trade-off. And here's where we are, the assembly, and let's look at some of them. So if we look at an assembly language, the very first thing we will look at is where the information is stored. In the C program, we store the information in the variables. Integer a equals to 10. Right? 10 is stored in the variable a. And then in the later program, we can write down for loop, whatever codes we can put down. So variables are the place to store information in C. How about assembly? Where we store these informations? Let's look at several places. The first place we will talk about is CPU. So you may notice the difference. When we talk about the assembly, where we store the information, it's a physical place. It's not a logical variable, but it's a physical CPU. The CPU have something called register file. It is part of the place to hold the information. And in these register files, you can, when we write assembly, we can access it. We can store information into the register file. And for register file, we need a name for that access them. The name we use is %REX, %RBX, RCX, RDX, so on and so on. In total, we have 16 registers for the CPU. So you may notice this number is quite small. Even now, this is for our modern computer. You look at a CPU, we just have 16 registers. And I can tell you, each register just have 64 bits. or 8 bytes in total. This is for each register. And we only have 16 of them. That seems quite small amount. So here we just clarify that these 16 registers are not used to keep your spreadsheet, not to keep your movie or whatever, something like that. It's not for like this purpose. It's just helping the CPU to execute. In such a sense, we don't need so much. We just need 16 of them to help the CPU. But they're quite be everywhere if you look at the assembly code. So let's quickly look at. So here we see that in assembly, we have the REX, RSI, RBP, RDI, RBP, ECX, things like that. That is the register. That's the register we talked about. We have only 16 of them. And for each register, you will get more used to this name, RAX, RBX, RCX, so on and so on. So let's look at each of the register. It has 64 bits. And then these 64 bits can be accessed by the %RAX in our example. If we write down %RAX, we're talking about the 64 bits right now showing in the dark red. Okay, this is 64 bits. And actually, sometimes we don't need to use up the 64 bits. Sometimes we just use 32 bits of it. Somehow it seems unreasonable, but yeah, sometimes we just need 32 bits from these 64 bits. We don't want to use all of them. What we can do? In this assembly language, if you want to access only half of the space, what you can put down is EAX. When you type RAX in the assembly, it means the whole space, 64 bits. If you type EAX, it is just the half of the same space, 32 bits. Sometimes we just need this EAX amount of data register. And somehow, if you just need 16 bits out of the 64 bits, what we can use is %AX. %AX means 16 bits. And if we just need 8 bits, what we can do is %AL. That means 8 bits of it. So there is a historical reasons why we divided the space into AX, AL, AX, EAX, RAX. So when we at the beginning, when we have the quite old computer many years ago, it's 8-bit computer. For the register part, it is 8-bit. In our example, we have the register called AL. AL is 8 bits. That was introduced many years ago. You can imagine our computer is developed continuously. At some point of time, we start to introduce the 16-digit computer. In such a case, each register right now is 16-bit. And that brings a problem. The old program, who is designed for the 8-bit, right now the program cannot be executed in the newer machine because the newer machine is right now 16 bits. In the previous one, just to have 8 bits. So we need to make it back compatible. How we can do that? So when people design the 16-digit computers, they just make sure the computer itself can be compatible to run the older programs. What do? They put down AX. AX for sure is denoting 16-bit register. Right? But in order to make the 8 in the older program be able to run, it also keep the AL to be the 8 bits out of the 16 bits of the register. So they keep the AL to be the 8 bits. So you can imagine when we have this kind of setup, if the program is for 16 bits, no problem. We have the AX, and when the assembly code have the AX, and then we can execute without trouble. But if the program is compiled and designed for the 8-bit, it uses the AL, which still exists in current computer. The outcome of it is this computer can not only run the 16-bit program, but also the 8-bit program as well, because they keep AL. Keep the AL, so we have the back compatibility. And you can imagine such a story just continues. We have the 32-bit machine. Again, now we introduce EAX. I would say extended, like EAX now is denoting 32-bit. And in order to make the previous programs runnable on the same computer, on the current computer, we still need to keep AX and also AL to fit or accommodate the 16-bit program or 8-bit program. So we just keep it. So right now we have the EAX and also have the AX and AL for historical reasons. Recently, we moved from 32-bit machine to 64 bits, and now we have the RAX to denote 64 bits. I would say, I don't know, maybe you can interpret it as a real AX, whatever. So RAX then means 64 bits. And because of the historical reasons, we still keep the EAX, still keep the AX, still keep the AL. So in our program, right now, we just have these 4 names, the same space, same 64-bit space, but we have 4 names to access the whole part of the register or some subpart of the registers by using other AX and AL name to access part of the binary. So this is the case for percent RAX. Similarly, for RBX, RCX, and the RSI, whatever, there's a 16 registers. We always have this 4 naming scheme to refer to parts of the data or all the parts of the data. So this is the registers. Any questions so far? Okay, let's just move on. Talk about registers. Now let's talk about another big place to hold data. That is the memory or RAM. If you buy a computer, you will see the RAM is 8 GB or 16 GB. The main memory is another place to hold the information. We already talked about for the main memory, the data is organized slot by slot, and each slot have the address of it. And in the slot, we keep the value. And the address will start from 1 until a very big number. Apparently, if you want to access a memory, we need to access by the address. So if we talk about, example, we want to look at the first slot, we need to have the address of it. It's a 0x1, 000FF0, right? This is the address. We use it to find the spot and then access the data. And the way we can use in our assembly code is put the address in the parentheses. So anytime in the assembly code, if you see a parenthesis, that means a memory place. Let me quickly show you what I mean. We just use this assembly code as an example. So we talk about REX. This is a register. There's no parentheses. So this first parameter is a register. In the second part, we have the parentheses right here. Anytime you see a parentheses, it is meaning a memory place. You can interpret quickly. We are moving data from REX, which is CPU register, to a memory location. Again, for the second line, you can see the RSI is the register. The second part is the memory place because we see these parentheses. Third line, minus 0x8, parentheses RBP, this is a memory, and RDI is a register because we have no parentheses for RDI, so on and so on. And we just put the address inside of the parentheses, and the format is look like it's just the red part. The format, if you write it this way, what we have is immediate value. IM is the immediate value. It could be a number. Immediate value plus I plus J times K. K sometimes we call scalar. This is how we calculated the address on the memory, and the whole expression is denoting that memory place. There is an example. If we have this RBX, REX2 in this format, and because we see the parentheses, the whole expression now is denoting the memory. And what is the address of the memory? We can look at the RBX right now is RAX times 2. So RBX is 0x 1 0 0 0 0 0 FF 0. RAX, if we look at RAX, it's 1. So what we have is 2. The address we are talking about is FF2. This is the address of the memory. So the whole expression is denoting a memory place right here. This is how we refer to a memory place. Somehow when some of the values are stored in the registers, and it's okay. Register is just something like your C variables. You just keep some value inside of it. It's okay. We use the registers in the parentheses, and this is how to denote a memory place in assembly code. And also, we have the immediate value. That's somewhere. Let's see. We want to move number 2 to register REX. Right? What are we going to do about this number 2? What we do is we just put a $sign in front of number 2 to denote it. This is the way the assembly denote a number. Just the $sign plus just $sign and number. This is how to denote an immediate value. Is there any questions? A question from Brogan. Will we need to memorize these abbreviations for the shorter forms, or is there a consistent naming scheme? Uh, do you mean the registers? Okay, yeah, I see. Yeah, we need to remember these registers. REX, RBX, RCX. You can have the full 16 registers, a list of the 16 registers in our textbook. I just show you several of them. My suggestion is you don't have to sit down and look at the 16 registers and to try to memorize all of them. In your practice, we will have practice. You will see these registers keep coming out, and then most of them you can get used to them within your practice. Yeah, but these names are finally after the class, we finally expect to know these names, what they mean. They mean registers. They mean somewhere in your CPU. Is there any other questions? Okay. We talk about where we store the information. It can be either in the registers or could be in the memory. In the next part, we will talk about the very first assembly instruction, which we call a move. Move is to move data between the registers in a memory. Right now, let's look at this example. In the previous assembly code, we talked about if we move, and then we have the format is we move from the source, S stands for source, to the destination. D stands for destination. So basically, move the data from source to destination. The source could be registers, could be memory, and the destination can also be source, can be also registers or destination, but they cannot be memory at the same time. So you don't have to remember this. You will understand later in the class why they cannot be memory at the same time. We will talk about it. So from the source to the destination, one question you may ask is, how about if I move the data from source to destination, is the data still available at the source? The answer is yes. You can imagine it to be a copy of the data instead of the physical move, right? We still keep data at the source. We just move the data. We just copy the data to the destination. It's called move. And then for the move, you can see here it also have the size of the move, which is specified with using B, W, L, and a Q. If the size of the move is for 1 byte, then you just put down B after move. This instruction together, move B, means move 1 byte from source to destination. And also you could move 2 words, then you put down W after it. L means 4 bytes. Q means 8 bytes. We just specify how much data we want to move from the source to the destination. Let me give you an example of how we determine the size of the move. So in our language, we, no matter what is the size of the move, we always have the move MOV part consistent, right? The problem is how we can make it determine what is the letter we need to put down for the size of the move. It could be B, means 1 byte, W, 2 bytes, L, 4 bytes, and Q, which is 8 bytes. And for the first example, which letter we need to put down? The way we can look at it is look at the size of the registers, which is EAX, and this size of the registers determine the letter. We talk about the EAX. EAX is 32 bits. In other words, we have 4 bytes for the EAX register part. And accordingly, we need to put down L after the move to make it a match. You may wonder, there's a RSP, this is a register as well, but notice that this RSP is in the parentheses. The whole parentheses means a memory place. We don't look at the memory place to figure out the size. We look at the register, the straightforward register, to look at the size. So we only look at the percent EAX part. We figured out this is 32 bits, and then we put down L at 8. And now let's look at the second one. We have the move. We need to pick up one letter from these 4 letters. We have the %dx as the parameter, %rax, but I put it in the parentheses as another one. So my question right now is, what is the letter we should put down here?
Q.
Oh, sorry, I cannot hear you.
Q?
U? A Q? Oh, sorry. Did you mean Q, right? Oh, I see. Yeah. Okay. So let's look at what is the letter we need to put down. We need to look at the register part. Should we look at the first register, which is parentheses %rax, or the second register %dx? Which part we need to look at? The first part or second part?
Second part.
That's right. Thank you, Dino. Second part is what we're gonna look at. And for the %dx, what is the size of it? We talked about RAX is 64 bits, and the EAX is 32 bits, AX is 16 bits, AL is 8 bits. Where comes this DX? D is from the RAX, RBX, RCS, RDX, right? So for the DX part, we are looking at this part. It is 16 bits. And for 16 bits, we'll look at the word, so or 2 bytes. So we need to put down W right here. This is the way we figure out the letter. Is there any questions? Okay, first we look at the, the parameters, which is the register, which is the memory place. Um, After figured out, we look at the register and figure out what is the size of the register, and then go back to determine the size of the move. Let's try another one. Let's look at the third example. What should be the letter we pick out?
It'd be Q.
Q.
It's the BL, which I'm going to assume is a B.
Okay, let's figure it out together. Okay, so we first look at which part is the register. We talk about FF, apparently is a number. And we need to look at the register part. So for this part, the register is BL. If we look at a BL, that's something about RBX, EBX, BX, and a BL, right? So the BL part is 8 bits. We figure out that BL is 8 bits, then we look at the letter we need to put down 1 byte, so we put down B over here. That's how we figure out the B letter. Is there any questions?
So sorry, I was thinking Q was the smaller one. Is B the smaller one in this case?
Yeah, that's no problem. So so the B means 1 byte. The biggest one is Q, that means 8 bytes. Yeah, thank you.
Okay, gotcha. Thank you.
Yeah. Let me write it down. B is 1 byte. And the W is 2 bytes. L is 4 bytes. Q is 8 bytes. Okay, let's look at the last one. What is the size for the move? Okay. Most of you get the right answer. So it is B. You may notice there's a lot of registers, RSP, RDX. Seems like there's a lot of registers, but keep in mind, there's a parenthesis. There's a parenthesis over here. No matter how many registers we put in, the whole expression, the whole parenthesis expression, they're denoting a memory place. It's not a register. We're looking at a register. So what we need to look at is %BL, the straightforward register. So the first part, no matter how many registers we put in the parentheses, we just ignore them. Okay, that's how we determine what is the letter of the move or the size of the move. Okay, before we talk about next part, is there any questions?
I have a quick question.
Yep, go ahead.
So if the amount of bytes that you're trying to put into a register is too large, does assembly automatically handle that, or is that something that we're like about to cover?
Oh, I see. Thank you, Isaac, for your question. So let me clarify. So if the data is too big for a register, is the assembly handle it or what happened after? Is that your question? Okay, great question. So you may notice in the real world, the data could be very large. That is handled by the assembly. Yeah. When you write down C program, like you write down a variable or let's say a struct, right? A struct could be many bytes. What's gonna happen? The register size is as large as 64 bits. What happened is assembly would chunk the data into different parts, and then smaller bytes. Chunk the data into smaller parts, and each time feed the CPU with the small bytes, and then CPU can handle it afterwards. So that's handled by assembly. Is that clear, Isaac?
Yeah, thank you.
Okay. Is there any other questions? Okay, let's move on. We want to move the data. Here's a quick example. I write down the C program exchange, give it two parameters A and B, and I want to exchange the value between them. What I do is I create a temporary variable C, and then assign the value of A to C, and then try to do the exchange. So this is quite a typical C program example. We want to exchange the data value. And then let's look at what does assembly code look like and what they're doing. And we first look at the yellow box, the yellow background part. The first of all, we move something. The first one seems like a memory place because we have these parentheses, and if we figure out the address of it, and write down here, the address of this memory place is %RBP. This is register, and -20. We do the calculation, and then we figure out the address of it, right? This is memory place. We move the value from memory place to EAX. And second one, move EAX to a new memory place. So you can already make a guess that let me clear that out. You can already make a guess here. The RBP -20, this memory location denotes A, right? Because in the C program, we need to copy the value of A to the variable C. So the data source is A. From here, we know the memory location whose address is RBP -20 is representing A. And the destination, which is RBP -4, should be C, right? And the EAX is just used as a temporary variable to temporary place to make the transition. And the reason we use EAX we talked about because we only have 4 bytes to move. EAX is 4 bytes. We just use EAX as a way to do it. So here we will mention that we cannot move from a memory place to another memory place. So we need to have these 2 instructions. Use the register as a bridge. And this is determined by by our computer architecture in the design. When people design the computer, design our CPU, it just prefer to have these 2 instructions instead of 1 instruction. Just try to make our architecture simpler to implement in our factory. If we want to really move from one memory place to the other, what we do is just break this into 2 instructions, move it to the register at first, and then from the register, move to the other memory location. The reason is just for simpler implementation for the CPU. By implementation, I mean manufacturing. Okay. So we have 2 instructions for move. If we look at the purple one, A equals to B, so we quickly can figure out RBP minus 24, that should be B, right? We move the value to EAX, again from EAX to minus 20, and we already talked about this, minus 20 is A, right? So it's consistent with the C program. The last step, we move B equals to C, and here minus 4, again, this is a C, and minus 24, RBP, this place is denoting B. And this is how we interpret a data movement right here. So this when you have the C program like this, we talk about there's a compiler. They will translate this C program into assembly code right here, what we show, right? And then this assembly, by looking at the mapping between assembly name to the number, then or machine level code, then we can further translate the assembly to machine level code, and that could be executable in your local computer. So this is assembly. This translation from the C to assembly is done by something called compiler.
I have a quick question.
Yeah, go ahead.
So for the move L minus 20 RBP, so for that line, the reason you can't just have it be minus 20 RBP and then comma minus 4 RBP is because it has to go to a register before you can change memory places. Is that correct?
The reason is you cannot directly move from one memory place to the other.
Gotcha.
That's a good question. So that cannot happen in one instruction. We have to break that into 2. That's not allowed. And let's quickly go back. So here, source and the destination cannot be memory at the same time. That means if you want to move from one memory place to the other, you cannot use one single move. You have to break it out using 2 moves. First, move the memory to the register. The second move from the same register to the other memory location. That's the reason. Okay, great. Is there any other questions? Again, it's not the reason why we need a 2 move instruction. We don't allow memory to memory move directly. It's just because the architecture design. It's just simpler to design in such a way. So that's a preference. It's not a self-imposed restriction. It's just the preference in designing the CPU architecture, and that as a result, as a programmer, we cannot move from memory to memory because that is not supported by the CPU hardware. Okay. Okay, great. Let's look at push and pop. Well, how many times we have now? Okay, we have another 15 minutes. For the push and the pop, it also is trying to move data by some way. And this push and the pop are specifically designed for stack. Some of you may have heard of this stack. And there's two understanding about the stack in computer science. If you learn the algorithm, there's something called a stack. It is data structure in your algorithm class. For the data structure, stack is kind of data structure, and the way to use it is last in, first out. Let me give you a quick example. If you put the data, push the data into the stack, it's like it's just like put your clothes in your laundry basket. First of all, we put the blue data. This process we call push. And next part, let's see, we want to push another data into this data stack structure because it's the black data. This is also called a push. And the third data, let's see, we push this blue data into, light blue data into it. And this is another push. Now, let's see, we already pushed enough data. Now we want to pop up. We want to get the data out of the data structure. And now we want to pop. This is where it comes pop. We get something out. We don't know what we get out. But based on the stack data structure, what we get out first is this data, the light blue data. This is the very first we get out. It's just like our laundry basket. You put your clothes into it, and when you want to get one out of it, you get the last piece you put in your basket. That's the stack. You can just think of it as a laundry basket. And if you pop again, you will get the black data. This is the second one, black data. If you pop it again, it will be the blue data. So this is an algorithm stack. In our assembly language, the stack is something not only utilizing the stack data structure, but it's a physical existence. There is part of the memory we use as stack. So it's a physical existence. We really have something that is in our memory, a chunk of the memory. We call that stack. For the stack in our class, it is introduced for implementing function call. So there is also a function call in assembly language. And in order to make it happen, we need to invent this stack stuff, invent a stack to make it happen. We'll talk later. And today we just know that in our memory, a chunk of it is called a stack. This is for function call. And for this stack, we have this push and pop instructions to move data around. Here's an example set up. Let's say this is a stack, and here is the register values we have. If we want to execute this push %EAX, we just push the data on the stack, on the top of the stack, right here. Right? And we push this data on the top of the stack, and because EAX right now is having 1, 2, 3, so we just put down 1, 2, 3 right here. And if we want to pop, sorry, let's clear it out. if we want to pop something out of the stack, we just move this 1, 2, 3 into EDX. So you can check after it, EDX is 1, 2, 3 because we pop the value to move the value to the EDX as a result. So this push and the pop are working on the stack. And you may notice there's a ESP we call the stack pointer. This is how we find the stack. Find the stack. Right now, the stack pointer is 108. We look at 108, and we figure out the top of the stack. And in our second example, we push something on the stack, and the top of the stack is updated to 104. The top has been changed because we put something in it. So the 104, and you can also notice the ESP has been updated to 104. So ESP is always pointing to the top of the stack. And it's also the way our CPU or our computer find the top of the stack, which look at the ESP. So here again, if we pop the 1, 2, 3 out of the stack, we go back to the original value 108. So this so the ESP or RSP for the 64-bit machine, that is pointing to the top of the stack. And you may notice here we have the EBP or RF or RBP that is pointing to the bottom of the stack. So for this stack, we can either find the top of it by looking at ESP or RSP, or we can look at the bottom of the stack by looking at EBP or RBP. EBP is for like 32-bit machine. RBP is for 64-bit machine. So base pointer, we call base pointer, or bottom pointer. So EBP is having the address of it. So the stack is kept in our memory. Is there any questions about stack?
Do smaller bit registers have the bottom and top stack pointers?
So could you say again?
So for something like AX, like how would we note the pointer for that?
I see. That's a good question. So for the RSP, RBP, these two registers are designed for the stack. And for like RAX, things like that, they're basically registers.
I'm sorry. I mean, so for like a smaller register, like AX, how would you denote the stack pointers for a smaller register?
I see your question. How stack pointer denote a smaller register? Okay, I see. So we see that the stack is kept in the memory. It's not in the register. So in the memory, we just have the slots, right? And then for the our stack or the stack pointer never points to registers.
Oh, okay.
Yeah, that's a good question. We don't point the stack pointer, no matter it's RSP or RBP, they point to somewhere in the memory. They don't point to the register, which is in the CPU. Okay, great question. Is there any other questions?
Not really a question. I just wanted to clarify real quick for my notes. ESP and RSP are the top, and then that EDP, or abbreviations of the bottom pointer. That's what that stands for, correct? It was EBP and RBP as well for the bottom?
EBP, RSP, Could you say again?
The abbreviations were EBP and RBP, and those were both the bottom stack as well. I just wanted to clarify for my notes.
Yeah.
And then RSP and ESP are the top.
Yeah, that's right. That's right.
And those always are pointed. Those aren't pointed to registers. You said those are in the system. Those are classified as stack pointers.
Yeah, that's right.
Okay, gotcha.
Yeah.
Thank you.
Yeah, no problem. Any other questions? Okay. Okay, this is the last slide. We have, let's see. We have 3 minutes, so let's just give you a quick summary about today's contents. So today we look at assembly code. We first introduce the machine level code. The machine level code is just a binary. In this binary can be recognized by the machine directly. When the machine see a 1, then that's high voltage. Otherwise, it's low voltage. By this way, the machine level code can be executed on any computer right now. But it's quite an inconvenient. We have to, as a programmer, we have to remember these numbers. Numbers is harder to remember, right? We need some name. So by naming the numbers, we have the very first language we human use, that is assembly language. By using the assembly language, it's easier for the programmer to write down codes. Before we execute assembly, we need a translator translate we call assembler translate back to the machine level code. For the information storage, we have 2 places in our assembly to store information. The first one is the register in the CPU. We have 16 registers in total, and each of them is 64 bits. For one example, RAX, we can access part of the data by using EAX, which is 32 bits, AX, which is 16 bits, and the AL is 8 bits. And also we can access the memory. Memory, we use the parentheses to denote it, and the equation to figure out the address of the memory is immediate plus I plus j times k. K is a scalar. And also we put a dollar in front of the number to denote immediate value. And the very first instruction we use is move. Move, we need to specify the size of the move. By looking at the register, straightforward register, we can figure out the size of the move. And also we talk about push and pop. These 2 instructions are specifically used to work with the stack. And the stack is a physical existence in our class. It's talking about a chunk of memory we allocate to use as a stack. And the push and pop is trying to push data on the stack or pop the data out of stack. And that's today's content. And thank you for attending. Next class on Thursday, we will back into classroom, and it will be in person. And if you have any questions, feel free to ask me. I'll be around. And thank you guys for attending.
Thanks, Professor. And you said we're in class on Thursday?
Yeah.
All right. See you then. Appreciate it.